but we'll just go straight to notation. So when it comes to 3-form methods especially, notation is really important. And you need to, during 1-2 methods, it's important that you start to get used to the different types of notation that you need to use in methods. Okay, it's important, and it's also basically the language of maths. So it's sort of the language that you'll be using for your maths. So really important that you remember your notation and you know how to use it. So here we'll be looking at set notation, function notation. So basically how to represent a group of numbers and how to represent functions in maths. Keep in mind, a set is a collection of objects. So in maths, I guess, a set is a collection of numbers. These might be familiar to you, intersections and unions. So if you have an intersection, it's basically a set of elements that are common in two sets. So for example, so it's denoted by this, and it basically means and. So for example, if I say how many people play basketball and soccer, that and tells me it's an intersection. So you're looking at people who play both of those sports. If I ask about union, I'm basically saying or. So how many people play basketball or soccer? So it's like you can choose this or you can choose the other. It can be either of them. Excluding. So basically here, we're basically saying how many people play basketball but not soccer. Here we're excluding people who play soccer. Another way I can exclude is I can say how many people play basketball but don't like playing basketball. So I'm excluding people who like playing basketball. So how many people play basketball but don't like playing basketball? And lastly, elementor. So this is basically if you have a set, you basically have stuff inside the set, so elements of the set. So for example, basketball and soccer are elements of sport. So they fall inside the set of sport. So they fall under the category of sport. So a Venn diagram is a really good way to visualize. So here is our intersection. So A is basketball, B is soccer. This intersection is something that falls into both categories, so basketball and soccer. Union, so this is union here. It can be A or B, doesn't matter. It includes just A, it includes just B, it includes the intersection as well. So when I say A or B, I'm talking about the union. And then excluding, we don't have a Venn diagram, but it's basically A, not B. Element of, so if I had a little category inside A, then this little blue thing would be an element of A. And a little tip, set notation is really, really important when we talk about domain and range. So we're going to come to that towards sort of the end of our lecture, but just keep set notation in mind. There's some sets that are already predetermined. So what that means is they occur quite commonly, and it just makes sense to give them, sort of assign them a letter to determine what they mean. So for example, we've got n, which is natural numbers. So that's probably the smallest set out of all of these. And natural numbers are your positive whole numbers. It's sometimes 0. Again, it's a bit of a gray area whether it includes a 0 or not. But in methods, you're not really going to be using, you're not really going to talk much about natural numbers. Z, so Z is something that does come up. So Z is integers, so it's whole numbers, but this time it's negative and positive. So remember, natural numbers is just positive whole numbers. Z is negative and positive whole numbers. So these natural numbers is an element of Z. So natural numbers are an element of integers because they fall under the category of integers. Now we're getting bigger. Q is rational numbers. So rational numbers are numbers that you can express as a fraction. So as P over Q. So for example, a half is a rational number because you can express it as a fraction. But pi is an irrational number because it continues. There's no exact fraction that you can use to represent pi. Another example of a rational number is a third. So anything that you can write as a fraction. And lastly, you have real numbers. So real numbers is all rational numbers, all irrational numbers, all the numbers that you can plot on the number line. An example of a rational number, so you have pi, you have stuff like a half, you have 3, you have -3, and so on. An example of a number that is not real, so something like square root of -1. So you can't have a square root of a negative number, that's not a real number. If you're doing spec, you're going to also have another category, a bigger one, with complex numbers and so on. But we don't care about that in methods. To represent a set of numbers, you basically use interval notation, or you can use this sort of brackets. So for example, to use these curly brackets, it's basically telling you particular values in that set. So if I say the set of even numbers from 1 to 10, I can use these curly brackets to do 2, 4, 6, 8, and 10. And if I use round or square brackets, so these are much more common. Round brackets, that's to indicate numbers that are up to, but excluding the endpoint. So if I say x is greater than 4, it's hard to use curly brackets. So it's hard to be like x is curly brackets 1.00001. Oh, sorry, not 1. 4.0001. 4.00. So there's just going to be so many numbers that are going to come up, and I can't possibly list them all. So we just say x is a subset of 4 to infinity, or x is an element of 4 to infinity. So basically, all I'm trying to say here is 4 to infinity are the values that x can take. These square brackets include. So they include that 4. The round brackets do not include. A little note, we never include infinity. Okay, so to make this easier to understand, I think it might be good to use, the greater than or equal to signs just to show what's happening here. So what this means is x is greater than or equal to 4 and less than infinity. So basically, x is greater than or equal to 4. What this here means is x is greater than 1 because it's a round bracket, so when it's not included, but less than or equal to 50 because it's a square bracket, that 50 is included. So that's basically how we're converting to interval notation. Okay. So this is greater than or equal to here. So to define a function, you basically need its rule and its domain. So this is the domain here. And the rule goes here. So your rule is the equation of the function. The domain is all the x values that the function can take. So a little bit of a summary. So this first f here, that is telling me that we are defining it as a function. So it's telling me that this whole thing is now being defined as a function. The AB is the domain. So function notation doesn't tell you the range, but by knowing the domain, by knowing what x values are there on the graph, we can figure out what y values are going to be there. And the y values are the range. The second R is called the codomain. So in methods, it's always going to be R. So don't worry about it. A common misconception is that people think that this R is the range. It's not. It's not the range. It's the codomain, always going to be R in methods. So you don't even need to bother about it. Okay, so f of x equals. So that's where we're getting the rule of our function. So here is our rule. So it's basically what process So what do we need to do to x to get the y value? And if you're confused about what a function is, it's a good idea to sort of think about it as a machine. So you have your input, which is your x value, and then you have your output, which is your y value. And you put the x value through that machine. So here, for example, you're putting an x value, multiplying by 2, adding 1 to get the y value. So you put that x value through the machine, it goes through it, and you're going to get the y value. A few exam tips when it comes to function. When you're labeling the function and giving the name and giving the dependent variables, be really careful. So you can't just go from f of x equals ax plus b. You can't just go from there to y equals ax plus b. You can't just go straight from there. You actually have to put something in between, such as let y equals f of x or something like that. So you can't just go straight from the first, so from this function equation to just y equals. So that's something to look out for. And it's something to look out for when you're doing inverse functions. And second thing, look at marks to see if domain is required in your answer. So sometimes people are write questions are like write the rule of the function or find the rule of the function. So when you're asked that, you just need to write the rule. You don't need to write your domain or anything. But if it says something like find the function of f of x or find f of x, if it asks something like that, it's most likely that you're going to have to write the domain as well. So if it says find the rule or anything about just the rule, then you just need the rule. But if it just says find, then you'll most likely have to write the domain as well. So the best way to know whether you have to do it or not is just look at your marks. So look at how many marks there are. Okay, so that's an introduction to function notation. If a function has to exist, then the rule must pass the vertical line test. So this vertical line test is not a huge part of the study design anymore. So it's not going to be tested, but it's good knowledge to have to decide whether something is a function or not. So sometimes if the function doesn't pass the vertical line test, we might have to restrict the domain. So we'll talk about that a little bit more later on. Essentially, for a function, every x value should have its own unique y value. And we use the vertical line test to check this out. So for example, let's see these two. Vertical line test intersects only once. Vertical line test intersects only once. So at any point on this graph, if you draw a vertical line, that vertical line is only going to intersect once. So this tells me that the function, so this is a function. Here, if I draw a vertical line, here at this point, it intersects once, but every other point on the graph, it intersects twice. So here, this is not a function. This is a function here. So you use the vertical line test. If it intersects more than once, it's not a function. Simple as that. So even if it intersects once here, at any point, if it intersects more than once, it's not a function. That's it. Okay, so that's it for functions. We'll come back to